Hello everyone. We're here with our presentation for social spider optimization algorithm for a nature-inspired computing course AAT. We will dive into what social spider optimization algorithm actually is, its applications, advantages, and disadvantages in this presentation. Let us go on to what social spider optimization actually is. Social spider optimization imitates the behavior of spiders that live on a shared web. It is classified as a nature-inspired meta-heuristic for complex problem solving. So in nature, spiders communicate using vibrations that travel across the web. So these vibrations help them detect threats, prey, and nearby spiders. So in the algorithm, each solution is modeled as a spider. So these spiders exchange vibration signals. So that allows the entire colony to search the solution space efficiently. So because of this cooperation mechanism, social spider optimization performs very well on complex, nonlinear, or multimodal optimization systems, where traditional methods may struggle. So now we have the biological inspiration. So where did this algorithm come from? So the biological inspiration behind this algorithm comes directly from real social spider colonies. So social spiders exhibit strong cooperative behavior. They hunt together, share resources, and support each other when dealing with large prey. So their primary mode of communication is through web vibrations. These carry important information such as presence of food, danger, or potential mates. Social spider optimization captures this communication mechanism computationally. So this allows spiders in the algorithm to share information and move intelligently and efficiently. So now we go into the actual mechanism and the algorithm. So in this algorithm, there are two types of spiders. One is a female spider and the other is a male spider. So in this algorithm, the artificial colony has two spiders. So female spiders make up about 65 to 90% of the population. So these are the main search agents responsible for exploring the search space and improving the solution. So male spiders play a supportive role in this algorithm. So there are dominant males who interact with females, while non-dominant males tend to follow the group and maintain diversity in the population. So this division ensures a realistic simulation of a natural spider colony, and it supports effective optimization. Now we have the rules for this optimization. Yeah. So a movement rules where it navigates the search space. Female spider movement. These female spiders adjust their positions based on the vibration signals. So they move towards spiders with stronger vibration signals, which represent better solutions. And they move away from the weaker ones, which have a lesser magnitude of these vibrations. So they are influenced both by the nearest better solution and the global best solution. If it's a male spider, then they behave differently. So if there's a dominant male spider, so these refine their position based on nearby females. So non-dominant males move towards the weighted center of the male population. To maintain the diversity of the population, they move towards the weighted center. So these movement rules maintain a balance between exploration and exploitation. So this concept is essential for effective optimization of any complex problem. Now we move on to the core mechanism, that is vibration and information sharing. The core mechanism that drives this social spider optimization is based on the signal or the vibration-based communication. A spider that represents a good solution emits strong vibrations. So these spread through the web and they attract nearby spiders. So this leads to exploitation of good regions of the search space. So the mechanism of this follows a simple pipeline, so which is a source, the propagation, perception of that signal, movement adjustment. So these through these processes, good solutions are influenced and they influence the entire colony, enabling a collective convergence towards the optimum. So now my teammates Ali and Chetna will take over the presentation by explaining the algorithm. Thank you.
Thank you, Anuj, for your informative speech. Now we'll move to the next slide, which is mating operation. So one unique feature of SSO is its explicit mating operation. Only dominant male spiders are allowed to mate, just like in nature. The mating radius determines male spiders are allowed to mate, just like in nature. The mating radius determines which females are considered. The offspring generated represent new solutions, usually better than their parents because they combine strong traits. Finally, if the offspring is better than the worst spider in the population, it replaces it. This improves diversity and prevents premature convergence. Now, moving on to the next slide, which is initialization of formulas. Now, let's look at the mathematical terms of this algorithm. This slide summarizes all the initialization formulas for sex distribution. Females make up between 65 to 90% of the population. Next is position initialization, where each spider is placed randomly within the lower and upper bounds of the search space. Finally, each spider fitness is calculated and the fitness weight is evaluated. These weights are later used in vibration and movement equations. The next slide is enhancing the things which we discussed in the previous slide, which is the vibration and operator formulas. Here we see the mathematical formulas. Vibration intensity decreases with distance, meaning closer spiders feel stronger signals. The female cooperative operator formula specifies how females move based on vibrations from best female, best male, or global best spiders. The male cooperative operator formula similarly defines how dominant and non-dominant males move. The next slide will look at the algorithms, which are the vibrations of the female operator. This slide breaks the algorithm into step-by-step actions. The step 5 is computing the Euclidean distance between spiders to determine vibration strength. Step 6 applies the female cooperative operator. If the random value is less than the probability factor PF, the female is attracted to good solutions. Otherwise, she repels from bad solutions. This dual mechanism ensures exploration and prevents stagnation. The next slide will look at the male algorithm and the mating operators. The step 7 defines male behavior. Dominant males move towards the nearest fit female, while non-dominant males move towards the weighted center of all males. In the step 8, it introduces the mating radius formula. If a female lies within the radius of a dominant male, mating occurs and produces offspring. This entire process increases diversity in the population. Now, moving on to the next slide, we'll see the update, termination, and output formula. Finally, the population is updated after all the movements and mating steps. Then the iteration counter increases, and if the maximum iteration haven't been reached, the algorithm loops again. Once completed, the best spider's position is returned as the optimal solution. Now, my co-teammate Chetna will take over from here. Thank you.
So this flowchart gives a structural view of the social spider optimization algorithm. So we begin by setting the initial values and distributing females and males. Then we initialize the populations and evaluate their fitness. Next, the algorithm repeatedly applies movement and mating steps until termination criteria is met. The visual representation helps understand this sequential process. Now moving on to the next slide. So this shows the complete SSO algorithm flowchart. So where it is summarized more clearly, it shows how the algorithm cycles between evaluating the fitness, computing the vibrations, moving females, moving males, and performing the mating operations. It also highlights the termination check before delivering the final solution. Now, coming to the advantages and disadvantages. So, advantages include a strong balance between exploration and exploitation, and simplicity and robustness, and the ability to tackle multimodal problems. Disadvantages include parameter sensitivity, computational cost, risk of premature convergence, and a lack of strong theoretical guarantees. So, despite this, SSO remains highly effective for many real world tasks. Now moving on to the applications of social spider optimization. SSO is widely used in engineering design optimization, wireless sensor networks, feature selection in machine learning, and bioinformatics scheduling. So its ability to model cooperation and communication makes it suitable for complex optimization problems where classical methods struggle. So as a conclusion to this, so we conclude that social spider optimization is a powerful nature-inspired algorithm that models cooperative behavior, vibration-based communication, and mating processes. Its diverse applications, adaptability, and simplicity make it a valuable optimization tool. Thank you.